Good morning, good afternoon, good evening, wherever you are, and welcome along to the AMETEK webinar, Solid State Controls this week. And this week we're going to have a unique opportunity for everybody to ask any questions related to their UPSs and DC systems. And what I'm going to do is I have a few questions from previous webinars that we've had, so we're going to start off with those, and then what we're going to have everybody do is if you have any questions, don't be shy, put them in the chat bar on the right hand side, and then we will go through as many questions as we can today. So as it says at the bottom there, this is your chance to ask questions. So my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solidstate Controls. Oh, before we go any further, just want to say to everybody, if you can hear me, please type in the chat bar so I know that you can hear me okay. So I have 20 years in the industrial UPS industry with various different industrial UPS manufacturers, all of the major ones. There will be a lag of around 30 seconds between me speaking and you hearing my voice. Basically, Webinar Jam is a platform we use, and they've got to send this broadcast out to Windows-based systems, Android-based systems, and Apple iOS systems. So there is some processing that needs to be done to the signal, and that takes about 30 seconds. So from the time I say something to the time that you type something in the chat bar is around about 15 to 30 seconds lag. Webinar Jam does have a panic button. We fortunately haven't had to use it yet, but if something crashes, if everything freezes up, there is a button that I can press, and basically what it does is it creates a new room and invites everybody back into that room, and we just continue from where we left off. So hopefully, once again, we don't need to do it today. The webinar will be recorded. We do two things with that recording. The first one is Webinar Jam will store that on its server, and if you registered for the webinar, you will then receive a link sometime after the webinar has finished, and that will allow you to go and view the webinar again. The problem with that webinar is it gets treated like a brand new webinar, so there is no fast forward, rewind, pause, or anything like that. Once you press play, you have to watch it as if it is a webinar. But our amazing marketing department, they go in and they convert that into an MP4, and then we upload it to our YouTube channel, and they will post a link to that in the chat bar so everybody has access to it. Most of our webinars last around 1 hour. Obviously today, we don't know how long it's going to last. It depends on how many questions that we get asked. And we have two special guests from the factory. We have Rob, our software designer, our software architect, and Doug, who is one of our seasoned engineers. So as the questions come in, I will delegate some of the questions, if necessary, to one of those two people. Okay. So as I said, the learning outcome today is just going to be open questions. So the first question that we had from one of our previous webinars was, please explain the pros and cons of using a diesel engine generator as backup with an auto transfer switch versus parallel redundant or a cascade system. So it's a very, very good question. So first of all, here is the most basic diesel generator backup that you can have that doesn't use a UPS, and many emergency lighting systems use a system very similar to this. So at the top, you have AC power coming in from the grid here. That goes into an MCC, and then the normal feed goes down into this automatic transfer switch here. And you can see in normal operation, the contact goes directly out to the automatic transfer switch's output, and then to an emergency distribution panel. And that's where you'll find your critical loads. And as I said, in this circumstance, it was probably going to be emergency lighting, because what happens is if we have a power failure and the grid power fails, then what happens is the automatic transfer switch will sense that. At this point here, it will sense that the voltage has disappeared, and it will send a signal, usually to the standby generator, to start. And if any of you have any experience with standby generators, the length of time it takes for a standby generator to receive a start signal to the time where it is fully running at frequency and at speed can be around about 30 seconds to a minute. So you are going to lose power at this point here at your critical load panel for about 30 seconds to a minute while the standby generator runs up to speed. And then once it does run up to speed, it sends a signal to the automatic transfer switch and closes this. So this will now be open, and it will close the switch here, and the emergency generator will feed the critical loads. Now, obviously, the biggest downfall of this is you are going to lose power for about 30 seconds. Okay, now that's okay for emergency lighting in some respects, but for critical loads like DCS systems and process controls, that's not acceptable. So the next page is a very common arrangement that we will see. And all they've done is they've put one of our AMETEK SCI UPSs on the output of the automatic transfer switch. Okay, so, and then our critical loads, so our critical loads are on the output here. So in normal operation, the grid goes through the MCC and feeds the input to our rectifier. Okay, that maintains the charge on the batteries and also supplies power to the inverter to convert the DC back into AC, and then that goes out to our AC distribution panel. And then what happens is if we have a power outage, the grid goes down, once again, the automatic transfer switch says, okay, start the standby generator. But during the 30 seconds or so it takes to start up, we have power from our battery through the inverter out to the load circuits. So we have continuous power. We do not lose power, at the output to your AC distribution panel. And then once the emergency generator is up to speed, and after the 30 seconds, this contact here closes, and we automatically get the batteries back on charge again. So they're ready if, for example, the let's say the standby generator fails, or you need to do something with the fuel. Then what you can do is you can stop the generator, or it's stopped automatically. We'll go back on battery power, and then you can do whatever you need to do to your standby generator while the batteries supply the load circuits. Okay. And then we have parallel redundant systems without any diesel generator, and this is a parallel redundant system. And what you will see is everything in red is energized and supplying load, and everything in green is just energized. So both UPSs, let's say this is UPS A and this is UPS B, they are connected together at this point here. Now, for simplification, I've drawn it without a remote manual bypass switch, but both UPSs are connected together, and they have logic between them that shares the load, and so they know what each system is doing. So, for example, if the inverter in UPS B fails completely, then UPS A will continue supplying all of the load without any issues whatsoever, and the static switch will know that UPS B has failed, and it will not try to switch UPS B on until it knows B is healthy again. Now, I suppose a lot of people when we're talking about pros and cons of any system, really the biggest concern is a single point of failure. And really, we have two static switches here, and then we have a third static switch for our bypass supply. So a static switch isn't a single point of failure for us here. Really, the only single point of failure for us here is the wiring between the UPS and the distribution panel and the distribution panel itself. That is the only single point of failure on a parallel redundant system. So it's actually a very good system for your critical loads. So that was parallel redundant. The person who asked the question also mentioned cascade UPSs. So this is a cascade UPS, and once again, red is supplying power or current, and green is energized and ready to supply if necessary. So let's call the primary UPS at the bottom here UPS A, and then we'll say this top one here is UPS B. Now UPS A is feeding all of the current required by the load. UPS B is keeping its batteries charged, but the inverter is on, but the static switch here is saying, okay, we don't need to switch on because we know that UPS A is okay. And in truth, what UPS B is doing is it is feeding the bypass for UPS A. Okay. So what would happen is if we had a failure and UPS A stopped feeding the load, whether the inverter had failed or something had happened, then the static switch here would say, okay, something has gone wrong with UPS A, and it would allow UPS B to feed load this way here. So once again, it's you will have UPS backup in both of those situations. And just like the parallel redundant system, you will have bypass supply if necessary, if both UPSs fail. The issue with this design compared to a parallel redundant UPS is you do reduce the points of failure become more apparent in a cascade UPS, because this static switch here and this static switch here are the only two that control power to your load circuits. This static switch for the bypass is behind this one. So this static switch could be a single point of failure if UPS B is supplying the load and it fails, and the bypass needs to supply power through this static switch. If that has failed, then you will lose power to the circuits. So that is the downfall of a cascade system. The pros of a cascade system is, if you ever needed to do this, is UPS A could be made by AMETEK SCI, and UPS B could be an older system that is a different manufacturer. So if you're trying to upgrade a system, you can actually have two mismatched manufacturers in a cascade system. Obviously, AMETEK SCI wouldn't recommend that. We would recommend that you have SCI UPSs for UPS A and for UPS B, but it is possible. But bear in mind, if UPS A is a 30 kVA UPS, then you have to make sure, no matter what the manufacturer is, the other UPS is of the same output rating. Okay. But the next page is the best case scenario for your critical loads. So this is what we would recommend. I hope most of our engineers would recommend this. So we basically still have our emergency power in the top left-hand corner here through the automatic transfer switch. And the emergency MCC feeds the AC input into the rectifier of UPS A. And the emergency feed will also feed the bypass of UPS B. Okay. And then on the other side, you will have your normal MCC, and it will feed the AC input to the rectifier of UPS B, and then it will feed the bypass supply of UPS A. So they are cross-connected. And what that allows you to do is, let's say for some reason the plant is doing maintenance on the MCC that feeds the normal board. Then you know that you have an emergency board which is going to be unaffected, which allows this UPS to feed critical load panel A, and also that will feed the bypass for this system over here. So both load panels will be supplied, even if you have a complete MCC failure. Okay. And the other good thing about this situation is, once again, we have 4 static switches available, so they are not single points of failure. And then, unlike a parallel redundant UPS, we have 2 critical load panels. So even if one of the critical load panels fail, or if the cabling between one UPS and one critical load panel failed, we still have critical load panel B operational. So this is by far the most robust design of UPS system that you can design for redundancy. Now, the only thing that you have to be careful with these types of systems is that you do match the load panel down here. So the loads on load panel A should all be repeated on load panel B. And this is really more for DCS systems more than anything, because most modern day DCS systems, whether it's Delta V or Yokogawa or whatever it is, they are now designed that the power supplies into the DCS systems have at least 2 AC inputs, if not 3 AC inputs. So if it has 3 inputs, you could have critical load panel A feeding input 1, critical load panel B feeding input 2, and then another grid supplied distribution board feeding input 3 on the DCS panel. And that way you get even more redundancy on your system. Now, obviously, there are design benefits for each of the methods that I've discussed before, and there is also cost implications for all of the designs. So in answer to the question, you know, which is better, which is worse, it really depends on what you're more comfortable with, what the plant specifications are for their parallel or their UPS systems, and how much money that there is in the budget for your new critical UPS design. So those are the 3 things that really drive the selection of which UPS design is best. But I would say, if you can have enough money in the budget to design your UPS like this one here, then I would always recommend that this is the way that you design your UPS system. So I hope that answers that question. Do bear in mind that as I go through these questions, you can ask more questions in the chat bar, and that way we can be ready once I go over this, the next question that was asked, to answer those questions for you. So the next question that was asked as part of a survey from one of our previous webinars was, what are the PM requirements for your UPS units, what they are and why they are important? What failures do they prevent? And once again, fantastic question, because a lot of people think that a lot of manufacturers just say, oh, you need to replace this, this, and this, so we can make money from you. And that's could be further from the truth. So let me explain what our recommendations are and then why we recommend it. So we have 3 major PM schedules for our UPSs. Now, we recommend that you do annual maintenance, and I'll go on and explain what that entails in just a moment. We also have a 5-year maintenance schedule that we recommend, and then we have a 10-year maintenance schedule. that we recommend. So in an annual inspection, this is very, very wordy because this is copied from our sales literature. But basically, this just lists everything that is done in an annual UPS. And a lot of people are surprised to find how in depth that we go into it. So really, the most important things are that we do a system cleaning. Dust and other contaminants are actually one of the main causes of failure in any electronic system. So as part of our annual maintenance, we power the system down and we clean and remove dust and contaminants that could lead to malfunction. And then we also check for evidence of heat stress, damaged, loosed, or failed components. And we not only do that by physically checking that, we call it the wiggle test. Our FSEs go in and they physically test each connection by wiggling it with their hand. What we also do now is every one of our field service guys, they carry a FLIR infrared camera, and we take pictures of all of the input and output terminations and anywhere else where power flows through the system to make sure there are no loose connections. And since we started doing this about 2 years ago, we have found many incidents of loose connections, and even where things have been miswired, and instead of being hot, they're completely cold when we expect them to be hot. So we do go through the whole system looking for connection issues. Obviously, if there's any parts in the annual PM, we would replace them, and I've got a slide for that later on. And then we do system operation and function testing. So we check all the inputs and outputs, the control circuits, the primary supply, the alternate supply, the charger, the inverter, the static switch outputs, and we make sure that they are all working correctly. We also test all the auxiliary contacts and the shunt trip circuit in the DC breaker by simulating a low DC voltage. And then we check as many of the alarm set points as we can to make sure if you do have a live alarm on your system that it reports to your DCS. We also calibrate all the voltages and current readings. We verify the free running frequency of the inverter. To do that, we switch off the bypass supply and we make sure the inverter runs at 60 Hertz plus or minus 2%. And then we simulate a full loss of power to the UPS, a complete plant blackout, AC input and bypass input. We make sure the system runs on batteries. Obviously, you have to have a remote manual bypass switch to do that, but we do that as part of our annual test. We check thermocouples, we check for balanced currents into the charger bridge. That's the biggest indicator of faulty SCRs in your rectifier, is if the input currents are unbalanced. We verify all the AC caps are good. We test the ripple current, go into the battery and make sure it's less than 5% of the ampere hour rating of the battery. And then we test charger float equalize functions, and we check operation of the inverter static switch. So you can see the annual checks that we do are actually very, very in-depth. Now, every 5 years, we do exactly what we just said for an annual, and then there are some additional parts that are recommended, which are in the table Schedule B, which I'll get to in just a moment. And then 10 years is our most invasive PM. To ensure performance and reliability, we replace all of the AC capacitors, the DC capacitors, the fans, the relays, and all of the PCBs. And I'll explain why in a little bit, but it's mainly down to DC electrolytic capacitors. They have a designed life from the manufacturer, and we calculate what that designed life is, and we say, okay, after 10 years, it goes past that design life, and therefore you have to replace them. So here is Schedule B. So you can see here annually, if there are relays, critical PC board relays, that's mostly on our analog and our microfarad systems. We replace those annually. any pilot lights. On our DPPs, we've gone away from pilot lights. So on our oldest systems, we will replace the lamps and the LEDs on an annual basis as well. We replace fuses every 5 years, fans every 5 years, alarm and system relays every 5 years. We replace the relays due to the manufacturer recommends the operation period of a relay due to the coil and the contacts is around about 5 years. We replace variable resistors every 10 years and all of the system capacitors every 10 years. And then down the bottom here, Schedule C is all of the PCBs that we change out every 10 years. And we'll explain that in just a moment. So for capacitors, capacitor life is listed in the capacitor manufacturer's data sheets by hours. Okay, and as I've mentioned there at the top of this slide, there are 8,760 hours in a year. Okay, so for this capacitor here, the ALS30, they're saying that they expect to get 40,000 hours at 85 degrees C, and that works out to 4.6 years. So for this capacitor here, we would recommend that you would replace it every 4.5 years. And that is not the case for our capacitors. This one here is 60,000 hours. That works out at 6.8 years. And this one here is 78,000 hours, and that's 8.9 years. Now, remember, I just took this from a random capacitor manufacturer data sheet, and that's for an 85-degree temperature. So that's where we get our time from. Our design engineers worked out for the special capacitors that we use at the temperatures that we operate our UPSs at. And the worst case scenario for those, I think, is 105 degrees Fahrenheit. Then we know our DC capacitors will give us 10 years of life. And that is why we replace them every 10 years. We know that our capacitors will last 10 years based on all the information that we have at hand. Now, if you don't replace the capacitors, this can be what happens. And this is a very good example of how much force is available in a capacitor that fails. You can see that you have a bus bar here. This is what it should look like. So this bus bar should be running parallel to those top bus bars. But obviously, this bottom middle capacitor here has failed. And what happened is the electrolyte inside the capacitor dried out. It started heating up. Pressure started building within that capacitor. And eventually, it ruptured quite spectacularly. And not only has it caused that force, and remember, this could have pushed this bus bar onto some other live conductors in the UPS. Not only that, but a lot of smoke would have been released when this capacitor blew. You can see that there is some residue here from this capacitor exploding. And in some circumstances, this can cause fire. And if that capacitor went on fire, then obviously the heat is going to rise to this capacitor here and go to these other capacitors here. And that can cause those other capacitors to go on fire. So heat and age are an enemy of a DC electrolytic capacitor. So that is why we recommend they are replaced every 10 years. Okay. Now for fans. The way fan manufacturers list their fan life is once again in hours, but they use the L10 life. And that is defined as the number of hours at which they expect 10% of the fans in operation would experience a bearing failure. Okay, and that number is obtained using test data and this fancy Weibull function statistical analysis. Never heard of that before, but that's what the fan manufacturers use. And basically it says bearings usually fail because of lubricant degradation over time, which is greatly affected by the ambient temperature. And then at this bottom here, you can see from a manufacturer, the service life L10 of the ball bearings can be taken as approximately 40,000 hours. This was for, I think it was a Pabst fan that I looked. Yeah, it definitely was a Pabst fan that I looked at. So 40,000 hours is 4.6 years, and that's at an average temperature of 40 degrees C. But they say, yes, this is an estimate, obviously. So once again, our designers looked at the fans that we use inside our systems. We went to the data sheet, we checked the ambient temperatures that we expect the fans to operate at, and it was decided that a 5-year span is suitable for our capacitors. So once again, I mean for our fans. Once again, we're not making these numbers up. These come from the manufacturers of the capacitors and the fans that we use. So that is why we have the schedule in place to replace them at those times. Okay. So now we are going to go to open questions. So you can ask any questions related to anything that we've discussed already, or you can ask any new questions. Just type them in the chat bar and we will see if we can answer them. So the first question I can see there is, we have AMETEK UPS systems that were installed since 2001 with original capacitors without issue. And that is a good statement. We always have to look at the worst case scenario. So once again, our data sheet for the UPS says that our UPSs can run without derating the UPS at 105 degrees Fahrenheit. So if you're running in a well-controlled temperature room at 70 degrees Fahrenheit, then that is going to increase the lifespan of your capacitors. And once again, you could have been lucky that your capacitors have lasted longer. They could. We do use a very reputable capacitor manufacturer, and they are built very, very well. But in truth, your capacitor is 20 years old. I wouldn't be, I know this sounds bad, but I wouldn't be proud that your capacitors have lasted 20 years. I would be concerned that your capacitors have lasted 20 years and they haven't failed yet. Because when they fail, you are putting the critical loads at jeopardy, because those capacitors could go on fire. I would never recommend going past 10 years. Doug, do you have anything to add to that?
At this point, you made the big point right there, Craig, and that ambient temperature has a huge impact on part life. If you're running in a very controlled environment, 2025 C, and the unit is not running at full load, obviously there's less stress on the parts, and we're getting out into the far end of the curve for the capacitors. So if you're hitting it with less ripple current due to lighter load, you got a lower temperature, definitely going to increase the life of capacitors. The downside is that that's in an area of the manufacturer's data that is indeterminate. When we go look at it and when we do aging analysis with one of our consultants, we have to assume worst case. And what Wasim put in there about what he's got there at his facilities, I think they've done a decent job of running these things conservatively and done a lot to increase the life. But we have the 10-year based on guys running them in less than controlled environments and at higher load factors.
And I think that's a very good point, is the ripple seen by the capacitors at higher currents on the system is going to decrease the life. And most UPSs are only out there running at maybe 30–40% load. But when we sell a UPS to anybody, we have to sell that UPS with the understanding that it is going to be operated at 100% load, because that's what it is designed for. So that's how we have to design the lifespan of all of our components. So the next question we have, actually it's a few questions. So to matching the rectifier current to the battery, is it correct that the rectifier can supply the rated current to a completely dead battery? In other words, the rectifier acts as a current limited power, which is short circuit protected. So since I've been speaking a lot, Doug, do you want to answer that one?
Yes. There's a lot of unknowns on this question, but if you have a completely dead battery, first thing you'd want to do is make sure that at least it's up to open cell voltage, which would be just right around 2 volts per cell on the battery. If you've taken it completely down to below about 1.6 volts per cell, you can connect the charger up to it and ramp the charger up into the battery. I don't know if you're going to be able to revive that dead battery. That would be the best way to bring the rectifier into a dead battery, would be to start the charger up, let it walk up into the battery, and let the current limit circuit on the charger limit its output so that its cell protection structure goes into place. If you go and take a running charger and you connect that dead battery to your DC bus, which is where the charger would be connected, you run the risk of taking down whatever other loads are on that DC bus, because what's going to happen is that the charger will immediately go into current limit, and that could take the DC bus voltage down to, if you're talking a 60 cell system, down to 105, 100 volts, while the charger goes into its current limit mode, then starts to pump current into the battery. The current into the battery is going to be limited by the internal resistance of the battery itself. And I'm going to also say, it looks like, based on the question, that this is a charger with a single output, so the charger's going into the bus, and there's no other feedback circuit to limit the current to the battery. That's on question 1. Question 2, John, could you clarify real quick? What kind of charge you have? Is this a single output or a dual output charger, like our DCR? If it's the DCR with the battery output terminals can limit the current going to the battery. There's a battery current limit on that. If it's a single output charger, whether it's a DCR or one of our analog controlled units, the only way you can control the current into the battery for charging would basically be to reduce the output voltage of the charger to the point that you're at the maximum current that the battery will take.
Okay. Now, yeah, I completely agree with what Doug has said. And this is a very common question. And as Doug stipulated, if you have allowed your batteries to discharge within the parameters of what most people deem as acceptable, which is down to 1.65 volts per cell, then you should have no problem ever putting a battery back on charge immediately, because our systems are designed so if you have a power failure, and say it's for 3 hours and your battery life is designed for 3 hours, then when the power comes back on again, that charger will automatically come back online and start charging your batteries and feeding your DC loads. That's what it's designed to do. And we do have short circuit protection with a fuse, and we have current limit, as mentioned, to protect the SCRs within the charger. So as long as there are no dead shorts on the battery, and as long as you haven't discharged it too far, as Doug has said, I never have any issues with you putting, let's say, for example, you paid for somebody to come and do a capacity test on your battery. They discharge that battery down to 1.75 volts per cell as part of that test, and you want to put that battery back on charge after the test has been completed. A lot of people get nervous about that, because especially if it is an older charger, when you put that charger back on again, you hear that charger going, and you get concerned. But that's what the charger is designed to do. So I have no problem with that. And then John has replied there, Doug, that assuming that it's a DCR.
Yeah, I saw that. So the DCR, I go back, and if you've got the type that's got the battery output with the battery current limit circuit, you can adjust that current limit point to whatever the battery manufacturer recommends. What I've seen for a lot of the valve regulators is 10%, maybe up to 15% of the amp hour rating. NiCads, depending upon which ones you have, again, typically they're 10%. I see them go as high as 20, depending upon the technology that's involved. And the flooded lead acids, again, they're in that 10 to 15% range. Depends on who you talk to at which vendor. That's why I'm kind of giving the range on those. And then the last question John asked was, can the parameters be controlled remotely? I'm going to say no.
I think Rob will have to answer that one.
I believe that's correct. I'm going to shut down my mic and let Rob answer that question.
So on a DCR, can you change the parameters remotely?
No, you cannot. There is a workaround if you want to hook a computer up to the DCR and maybe remote into that computer. You could use our SCI Link software to do that, but we don't recommend leaving that connected all the time, just because the USB cable coming out of the DCR can act as an antenna and induce noise into your system.
Yeah, and the main reason for that, John, is it's very, very difficult for people to allow any of their systems to be connected to a network that connects to the internet or the cloud. So one of the things that we have to prove to our clients is that if somebody managed to hack into your system and get into our controls in our software, is there anything that they can do that could jeopardize the load circuits? And if I am correct, Robbie, there is nothing anybody can do remotely to jeopardize our loads.
No, our communication package with the Ethernet is read-only. It is a totally different processor than our. It's attached to our display board, but the processor is completely separate, and it uses proprietary protocol to communicate with the DCR, and the protocol does not have any hooks for it to change any settings at all.
And the last thing that John has asked is, can equalize be initiated remotely?
On a DCR, I do not think so.
You don't think so? Okay.
No, at least not. You'd have to use like some kind of being a dry contact input to the system, and I do not believe we do that.
Okay, sounds good. So Matthew has asked, this is for you again, Rob, are AMETEK Solid-State Control units fully capable of being connected to an internal network system for the purpose of remote monitoring and alarm reading?
Yes, we offer a few different ways to monitor. We have Modbus RTU, which is on an RS-485 copper cable. And we also have Modbus TCP, which is Modbus over Ethernet. We have an internal web page that you can monitor. And then we also have some other options. We have SNMP, and we have, I'm missing, Profibus and IEC 61850 options.
Cool. Good to know. This is maybe something for you to comment on, Doug. Oh, wait, there. Yep, Matthew's just saying it is read-only. Yes.
Yes, everything remote is read-only.
Yeah. So our friends in Croatia are asking, Doug, in the aging analysis performed from SCI, we can see that operation life for capacitors can be longer than 10 years. Please comment. I think we actually covered that. You agree?
Yeah, because the aging analysis that he's referring to has to do with the specific criteria at a nuclear power plant.
Yes.
And while some of the capacitors can go longer than 10 years, we're conservative in our recommendations, especially in a nuclear power plant because of the safety-related function of the UPS. We would much prefer to do a proactive replacement of the capacitors rather than try to run the capacitors up to end of life and then change them out.
I agree. And I will state that obviously I'm from the UK originally, and there was a UPS room that did go on fire in one of the nuclear power plants in the UK due to electrolytic capacitor failure. They had a very bad day that day, and that just goes to show you that I'm sure the aging analysis was done on the capacitors that were inside there, because the nuclear regulations are just as tight in the UK as it is over here. So they must have ran them right to the edge of their lifespan, and some failed, unfortunately, and did cause their UPSs to go on fire. That was a long time ago, but it does happen. So we do have to be conservative for those reasons particularly. Could you talk about the reasons one might order the 12-pulse option on a charger? Another one for you, Doug. I think that's a good question.
Okay. Yeah, the 12-pulse charger has two benefits. John alluded to one, which is you have a lower output ripple voltage. The other advantage to a 12-pulse charger is that the AC input current harmonics are typically less than 12%. A lot of times with our equipment will be under 10% THD current at full load. And for plants that have a limited capacity AC bus, limiting the harmonic current distortion is a big help. The second part of that is with the 12 pulse, the raw AC voltage coming out of the bridge is a lot lower in amplitude, so it makes it easy, and it's also at a higher frequency, 720 hertz. So that makes it easier to filter. The second part of that question is if it's okay on chargers. Either way, a 6-pulse or a 12-pulse is okay. You typically need some filtering out there for the batteries. If you go back and look at the NEMA standard, which was the industry here, at least in the U.S. For many years, the recommendation of the NEMA was that you should have a filter charger when you're running on batteries to limit the ripple voltage and/or ripple current into the battery from the charger. That's the biggest advantage. With the 12 pulse, the filtering, it's easier to get to a lower ripple voltage value versus a 6 pulse charger. Anytime you reduce the ripple on the DC bus, you're going to have less impact on the batteries themselves.
Yep, absolutely. And in truth, you know, if you go back 10, 20 years, if you connected your charger to a wet cell battery, a lead acid battery, where you can see the electrolyte and you can top it up, a lot of chargers were designed without filters because, as many of you will know, a battery, because of the plates inside the cell itself, act as capacitors. So it actually gives you some form of capacitance or filtering on that system. And the ripple was higher on those systems, but because the electrolyte had a higher volume and you could top it up, the only detriment to those cells was that it did cause the water to boil off a little bit quicker than it would if you had a filtered charger. But with valve regulated batteries, you cannot do that because there is no free electrolyte in the valve regulated battery. So high ripple on a valve regulated battery can, basically what it does is it's constantly discharging and charging the batteries. And for a 6 pulse charger, it's at 360 hertz, and for a 12 pulse charger, it's 720 hertz. The lower the frequency of the ripple, the more damage or the more heating it does to the battery. So, and that's what kills valve regulated batteries, is heat. So if the ripple current is high in a valve regulated battery, that can cause the internals of that battery to heat up. And when a battery heats up, you're actually supposed to supply a lower voltage to that battery because it will accept more current, just because of the design of the chemical design of a battery. And that is what can eventually cause two batteries going into thermal runaways, because they heat up. They're supposed to get less current, but because they're heating up, they actually get more current unless you reduce the voltage, and it just snowballs that way. So that is why you should always have a good filter on your charger when you're connected to valve regulated batteries. But I will caveat that, because I did see a white paper that was produced by one of the other manufacturers, the UPS manufacturers, last year, and it said that they only saw a 1.5 to 2 degrees Fahrenheit increase in internal battery temperature with I think it was a 50% higher ripple going to the battery. So there's still a lot of unknowns when it comes to batteries, and battery manufacturers are also always extremely conservative because they're really trying to protect their warranties. So I hope that answers your question and didn't confuse you anymore. Off the wall question: what is the life expectancy of solid state controls UPSs, and how long are spare parts planned for? Do you want to give that one a stab, Doug? It's a contentious issue.
Sure. Design life for the equipment is typically 20 years. Nuclear equipment, we have to design for a 40-year lifespan. We keep spare parts on hand for the life of the equipment. That's probably a big part of my job right now, is some of these older systems out there, parts people have either quit making the parts or have gone out of business altogether. And the challenge is always to try and find a form, fit, function replacement. Also, we have ongoing improvements to the control boards and to some of the other parts as well. And so, for example, on some of the old analog systems, for the inverter, we've gone from literally individual parts, transistors, capacitors, and what have you, and actually have gone into more of a CMOS logic-based type circuitry. So the board itself, drop-in replacement, but definitely doesn't look like what was put in 30 years ago or 35 years ago. So game plan is that we will support the equipment for its design life. Standard equipment is just 20. I've seen them go 30 plus years on a lot of this equipment. Nuclear stuff is 40 and 40 years at this point.
Yeah, agreed. Our guys, I know that we went out to a system that was built in the early 70s this year that is still running. So like Doug said, design life is 20 years. But the fortunate thing that any SCI customer gets is the fact that for the analog systems and for the nuclear approved DPPs, which is the NPP, as soon as it becomes nuclear approved, like Doug says, we have to support that for 40 years. So that means we will be supporting all of the DPPs while the NPP is still covered. So the fact that we get nuclear approval for our equipment makes it much better for our clients, because they know that our equipment is going to be supported for a much longer period of time than some other manufacturers. Do you know which nuclear power plant installed your UPSs instead of new MG sets? Ooh, I haven't heard of that, Doug. Have you? But I'm sure.
See, I'm not aware that the NDPP was installed instead of an MG set. I don't remember that in the run up to the site that they're going in right, or the two sites they're going into right now. Those are actually replacing old UPS systems.
Yeah, I think what that person is asking, and maybe we can contact them privately, is when they say NPP, I don't think they're talking about the nuclear DPP. I think they're saying which nuclear power plant installed one of our UPSs instead of a new MG set. So I wouldn't want to give that information out to the public anyway.
Yeah, and the other thing is that at least, and this is not speaking anything out of school, but I'm not aware of a situation where we've been either replacing an MG set or where there's been an either or situation when we've done that here, at least in my short period of time being involved directly with the nuclear product line.
Okay, so we have a couple of minutes left. So as they say, if you don't ask your question now, forever hold your peace. So we'll give you a few more moments. If anybody joined us late, I would like to repeat, this webinar has been recorded. It will be available on our YouTube channel, and our marketing department will post a link in the chat that will show you where to go to get to our YouTube channel. Also, everybody who has been part of this webinar will be sent a survey, and we really do read every survey, and we do want to know what you want us to talk about at our next webinar, because we can go on for days talking about stuff and nobody's interested in it. I don't mean that in a bad way, but I'm much more interested in giving you the information that you need, which is actually one of the reasons why I did this Q&A session today. I want to help you guys out there by answering questions that you have, rather than me telling you stuff that you maybe don't want to know. So Taylor has put in the YouTube channel there, and we've got no more questions coming in. So Doug, I would like to say thank you very much. And Rob, thank you very much. Oh, he fit one more question in. Very good. Parallel redundant versus cascade redundant. Any preferences or comments? Doug, do you want to? I have my own ideas. Do you want to say what you prefer?
Depends on your operating philosophy. We've done both over the years. I've got a site that's pretty much all they put in was Cascade redundant, and we've got other clients that prefer the parallel redundant. It all really comes down to what is your preference. We can do either, and that's what we offer them.
Agreed. And it is down to preference, or sometimes what's written into the plant's specifications for UPSs. Cascade redundant is much easier to do because there isn't complicated logic that has to go between the two UPSs. In truth, the two UPSs don't really speak to each other at all in Cascade redundant applications, but in parallel redundant, they absolutely have to speak to each other. That is complex electronic circuitry, which is very reliable these days. So it really does. It depends on what your preference is. If you pushed me against a wall and put a gun to my head, I prefer Cascade redundant. As somebody who works on UPSs in the field for a long period of time, it's just much easier to isolate one system in Cascade redundant and do work on it. It's just down to the maintenance. It's much easier to work on a Cascade system, but that's just my personal preference. Okay, so I was saying, Doug, thank you very much, and Rob, thank you very much. You have any comments before we go?
No, Craig, thanks for the opportunity to join you today.
No, thank you for taking time out of your day to do this. And the same with you, Rob.
Yep, no problem. I don't have any comments either.
Cool. Well, we will end, goodness me, pretty much on time. That's amazing. First, thanks again for taking the time out of your day. We do appreciate you're very, very busy. And for you to take an hour out of your day and watch this webinar, we really, truly appreciate that. You can go to our website. Taylor has posted all the information that you need in the chat bar there. If you need any further information from us, use the SCI marketing email or go to the Solidstate Control's website, and there's a contact form on there. And you can call us, 1-800-635-7300. So until next time, thank you very much for joining us. It has been a pleasure, and take care until our next webinar next month. Thanks very much, everyone.